Hello, welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as just new discoveries that point to the reality of God's existence. Hi, my name's Jeff. I'm going to be your guide today as we look into some kind of catastrophic events that might happen in the universe or that have happened. But before we get into that discussion, I want to encourage you to subscribe to our channel, Reasons to Believe. Click on the bell icon so you can be informed of our new videos. Learn more at reasons.org or by following us on social media at RTB_official. Hugh, good to have you here today. I know you've been out traveling, and it's good to kind of be back in the studio and do some recording here. I know you've got something that's at least catastrophic, so I'll let you go ahead and start the discussion for us today.
It looks like we both are going to be talking about something catastrophic, so a little different area of the universe. So, this is a paper that got published in the Astrophysical Journal Letters by a large team of astronomers where they have discovered a new kind of object, a new kind of risk for life in the universe. And the technical term they came up with, they've yet to come up with a really good name for it, but they refer to it as luminous fast-cooling transients.
Well, that's dull.
That's really dull, yeah. I'm sure they're going to come up with a name like a pulsar or something like that for it, quasar. But so far, that's a new discovery, so they've yet to come up with a good name for it.
Luminous, fast-cooling transients.
Yes.
So it's obviously something very bright, relatively quick.
That's it. You got it.
Okay, all right. And transients. Okay.
And it was discovered by the Atlas group. And ATLAS, let me read what it actually stands for. Asteroid Terrestrial Impact Last Alert Survey. And you say, hey, this thing is trying to find asteroids. But they said, hey, they looked at the data and said, we're going to look for supernova in distant galaxies. And that's how they discovered a new category of a cosmic explosive event.
So this isn't just a supernova, but it's at least akin to its behavior in some sense.
Well,
I presume that's why they're sensitive to things like that.
Right. And they've only found 3 of them.
Okay.
And they're in distant galaxies. But what surprised them is that they're in galaxies that are passive. And that's a term for a galaxy that long ago has stopped star formation. So these are galaxies with old stars.
So is because generally I think passive would be the converse of active. You've got active galactic nuclei. That's where the interior of the galaxy is feeding, and that's what it is. So it's not passive in terms of that. It's passive in terms of star formation.
Passive in terms of star formation. So these are galaxies that have long ago stopped forming stars.
Okay.
Because when you see something really luminous and it's relatively brief, you immediately think, oh, supernova or a new kind of supernova. But only really big stars go supernova,
right?
And big stars burn up quickly. And these passive galaxies don't have big stars. So it's like, it doesn't look like it's a supernova. I mean, and we're finding them in galaxies where supernova shouldn't be occurring at all.
Interesting.
And the other thing, as I said, it doesn't match the characteristics of a supernova. For one thing, it rises very fast and dims very quickly.
Meaning what? Because, supernova do that on the order of 30-ish days.
Yeah, this does it in 9 days.
9 days, okay. So not much faster. Okay.
Goes up to peak brightness much faster. And the really distinguishing factor, how quickly it fades. So its luminosity drops by a factor of 6 times in just 15 days. Okay. So it's like this gets really bright quickly and then dims very quickly. And the other thing is the peak brightness is 16 times higher on average than the peak brightness of a Type 1a supernova.
Wow. Okay. So these are very bright. They're just much faster. Okay.
Because Type 1 supernovae are your brightest supernova in terms of their peak brightness, and this is 16 times brighter than that. And so they were just saying, what are we dealing with? Because it's like we've never seen anything like this before.
Okay.
And if it's not a supernova, what is it? And the first thing they looked at is, well, maybe it's a supermassive black hole that's consuming a star. That might explain it. But what they discovered is that these events are taking place at 13,000 to 32,000 light years from the centers of these galaxies.
Okay.
And it's like, there aren't going to be any there aren't going to be supermassive black holes anywhere except at the center of the galaxy. So they said that explanation doesn't work. And so they looked at 6 different possible explanations for this new phenomena, but they were able to discount all but 2.
Which are?
The 2 that remains is a stellar mass black hole, not a big black hole, but one that weighs a few times more than the sun.
Okay.
So basically a supergiant star that went supernova and wound up as a black hole that comes in a few times the mass of our star, the sun. And where that stellar mass black hole is having a collision with an ordinary mass star. So,
Okay.
Because, these galaxies are filled with stars like the sun and stars that are smaller. And so if you get a collision event where the black hole is basically absorbing a medium mass or small mass star, that could explain the phenomena.
Well, that's kind of interesting because, as a general rule, stars don't collide, and so
No.
you think, okay, even in galaxy collisions, the stars tend to not collide.
Well,
so, what would
these
any idea
passive-
what would be causing that? Or
Yeah, well, passive galaxies are typically galaxies that might have been spiral, but the spiral structure collapses and they become an ellipsoidal galaxy where the star density is high.
okay,
Or it could be a galaxy that's filled with globular clusters where the star density is really high. And these, like a typical globular cluster has a few 100,000 stars within about 10 light years.
okay,
So, where we are, you got to
you're
go.
like 12 stars in 10 light years.
Exactly.
Okay.
So, a very high density of stars where you actually have a possibility of these collisions.
Gotcha. Okay.
And the key factor in their modeling is they picked up another observational clue, and that is these 3 events, very bright optical luminosity, but they were not able to detect radio radiation or X-ray radiation.
Okay.
Again, that's another reason why they ruled out a supernova. With a supernova, you get radio radiation, you get X-ray radiation. Here you get very bright optical radiation, but not the radio or the X-ray, or at least not at a detectable level.
Yeah. Okay.
And so that's why they were saying, well, we can actually explain the very low radiation of radio and X-rays if it's a small black hole absorbing a relatively small mass star.
Okay.
The other thing they looked at were intermediate mass black holes.
So this is like 30 to 100 solar mass type things, or larger than
A few thousand.
few thousand. Okay.
Yeah.
So this is just not up at the millions, which would
Not
be
up at
the
the millions,
supermassive ones.
which would
Okay.
be the supermassive black holes. Intermediates are at the low thousands.
Okay.
And stellar mass are a few times the mass of our star, the sun.
Right.
And they said their modeling more favored the stellar mass black holes than the intermediate black holes, intermediate mass black holes. But where you're going to have a high star density is in globular clusters.
Right.
And globular clusters have intermediate mass black holes. So
Is there enough? Okay, so they found these events. Can they tell whether they're in globular clusters, or are they just far enough away they can see they're in a
far enough
galaxy,
away
or
they can't
even
tell.
identify what's going on or where they are
They
yet?
do know that, spheroidal and ellipsoidal galaxies typically have a lot of globular clusters.
So they can see enough to know and identify that they're in these passive galaxies, though,
right.
correct? So,
They
okay, so
know
there's some
that.
sort of observations. It's not just you're seeing the transient itself, you're seeing the transient and the environment at some level.
Well, also keep in mind, Jeff, at the end of the paper, they say we've only found 3.
Right.
To really see what we're dealing with, we need a lot more observations. So we found a new category of astronomical object. Nothing like this has ever been discovered before.
Right.
This is like a new research endeavor for the astronomical community. And basically, let's find out more details about what these objects really are like. It kind of reminds me when they discovered radio burst events. It's like there's a lot of speculation. What are these things? And it took a lot of follow-up observations to really nail down what we're dealing with. Basically, they're saying the same thing is true here. We need to do a lot more research. But they said our initial results indicate these objects are relatively rare.
Okay.
For obvious reasons, nobody discovered them before, so they
Right.
could be somewhat rare. And they did an initial calculation of how frequently these events occur. And it's like 1 per cubic gigaparsec per year.
Okay, so how many in our galaxy would that be, or how often would one occur in our galaxy?
Well, not very often, because a gigaparsec is, 3.26 million light years. So that's a lot of...
A lot of galaxies you're encompassing in that.
you're
Okay.
looking at hundreds of thousands of galaxies. And what they pointed out is that if this actually stands up as a true rate, it's about 100,000 times less than the core collapse supernova rate. And, we see about one of those every century in a galaxy.
Right, okay.
So to answer your question, that's about once every 100,000 years you'd see one in a galaxy like ours. So although they said, based on their study, you're probably not going to find many of these in a large spiral galaxy because you're going to need to have the star density high enough where you got the possibility that one of these smaller black holes could have a collision event with a star.
But, I mean, we have a reasonable number of globular clusters in our galaxy. Presumably, wouldn't we have those intermediate mass black holes there?
Well, what they didn't address in the paper that caught my attention, this has a potential to deliver a lot more design features that explains why we have advanced life in our Milky Way galaxy. Because one of the special features of our Milky Way galaxy comes in at 1.2 trillion times the mass of our star, the sun. So we live in a big galaxy.
Right.
But it has only 152 globular clusters.
Okay.
And
So that's actually a relatively small amount, considering how large our galaxy would be.
It is, because galaxies our size typically have thousands.
Right.
I mean, I think M87 has got like 15,000 globular clusters. And, it's definitely more massive than our Milky Way galaxy, but not that much more massive. And so we're under-dense with these globular clusters. And the core of our galaxy, the star density isn't as high as what we see in other large mass galaxies. So this is additional evidence that our galaxy is fine-tuned. We live in a local group of galaxies where the galaxies are far enough apart, and there are no big passive galaxies in our local group, so that lowers the risk that we would be exposed to the radiation from these events.
Well, I mean, couldn't you argue at some level? I mean, I think these are just fascinating and cool, but at some level, these are cool but benign events in the sense, if I remember you correctly, you said they don't give off a lot of X-ray emission. They don't. It seems like most of it's concentrated in the optical, which would mean you'd get bright flashes of light, but not a lot of other consequences to it.
Yes, that's true. They haven't looked at gamma rays, so it's like, okay, we need to look at the whole spectrum to see what we're dealing with. But that's a potential another design feature. These things are very explosive and dramatic, but not that risky for advanced life. But these has a caveat. We haven't studied the whole spectrum.
Fair point, yeah, no.
And we don't know the actual rate. I mean, because they were very cautious saying, this is just a guess of what the rate is. We're working with a sample size of 3.
Yeah, you got to be careful extrapolating from 3.
And, we just discovered these things. And if we're looking at, say, radio fast bursters, they thought they were extremely rare. And they discovered they weren't as rare as they initially thought. So they said, we need to do, and hey, they found it by accident, sort of, by looking at using an instrument that was designed to detect asteroids. They said we could really follow this up by seriously focusing on this new kind of object, and then we'd actually have a true population statistic for these objects.
Out of curiosity, why do the supernova projects not pick these up? The one would think that they look a lot in that they would see these optical transients and would have detected them. Do you have any insight did they give on why maybe the supernova searches hadn't revealed this?
They didn't comment on that in their paper, but I was saying, the instrument they use, the Atlas instrument, it's really good at picking up things that happen quickly.
Okay.
The supernova things, they're saying, supernova, we can see them for about 7 months.
Okay.
And so given that you got that long of a window, that might explain why Atlas picked it up, because Atlas is a better instrument for finding things that are bright for just a short period of time.
Okay.
And also the fact that Atlas is focusing on optical wavelengths, and these things are really bright at optical wavelengths. So, but again, that's just a guess.
Right.
Keep in mind, this is a brand new discovery of a brand new kind of object. Similar, you're too young to remember this, but I remember when pulsars were first discovered.
Right.
There was a huge mystery. What are these things? What are we dealing with? It took years before they really had a good understanding of what they're dealing with.
Right.
I think the same thing's true of this. This is opening up a whole new discipline of astronomy.
Well, and it's fascinating. I mean, you come up, it's not every day you come up with a new type of object, especially something that, if this is or stars and black holes colliding and giving off stuff, that's pretty catastrophic stuff. And to just now be discovering it is kind of cool. So,
I mean, the discovery of pulsars led to a couple of Nobel Prizes.
Right.
This might be a Nobel Prize thing because it's really a whole new category of astronomical phenomena. Definitely fascinating and interesting, but also think it's got real potential to demonstrate that there are design features of our galaxy group, our galaxy cluster that might explain why advanced life is able to survive here on planet Earth. Because the number of big passive galaxies within our vicinity is really low. There's none of them in our local group. And the galaxy groups that are closest to us, also, we don't see any of these objects. You got to get to the Virgo cluster before you see them. And the Virgo cluster is, 50 million light years away.
Right.
So the risk factor drops. So I see some interesting design possibilities here. But again, very tentative.
Yeah.
We don't know a lot about these things yet. And we haven't yet studied the whole spectrum. We don't know the population. But it's kind of like, let's wait and see. But I think this has real potential to strengthen the biblical creation model that we're developing here at Reasons to Believe.
No, that's fair. And it also strikes me, I mean, to me, there's an apologetic significance in this, or apologetic import in this, just that, with as much as we've been studying, my question about the supernovas, why didn't they find them? It's like, it seems like there's always new stuff to find. I mean, this isn't like, oh, there's some more, mundane stuff. It's like, here we are doing this study of things that we studied quite a bit. I mean, we studied a lot about asteroids. We studied a lot about supernova. And here we are discovering something pretty significant and interesting that we didn't even know to think about, 10 years ago.
It takes me back to my graduate school days. I remember my first year of graduate school, the professor saying, in astronomy, there's a high potential for serendipitous discovery. But you as an astronomer have to be, attuned to that possibility. Don't overlook things that seem not to fit. And, that proved beneficial in my own PhD work because I found a couple of objects that basically didn't fit anything that people thought was standard astronomy. It was really new stuff. But being open to finding something serendipitous can be very fruitful in astronomy. And this is a serendipitous discovery. Who would have ever expected that a telescope that's focused on finding asteroids would find things billions of light years away?
That seem to be pretty catastrophic explosions.
Right. And it was Neil deGrasse Tyson who said, the universe is out to kill us. So
there's a solid point to that. I mean, it's hostile and friendly to life at the same time. So
it's friendly here on planet Earth. It's hostile everywhere else, and this is a new hostile, new piece of evidence that the universe really is a dangerous place.
Yeah,
but we happen to live in a protected region. So.
Very good. Anything final to add? No, I appreciate that. Okay. So, switching from one hostile environment, actually, you can make an argument that the Earth's been pretty hostile to life because, one of the things that we see is that Earth repeatedly is bombarded with asteroids, comets, things that just cause a lot of destruction. In fact, one of my favorite images on the web, it's got a meteor crater out in Arizona. And, it's like, it's got that. And it's like, wow, look how close. It almost wiped out the visitor center. But
have you actually been there, Jeff?
Yes and no. So we were on vacation one year and we thought, oh, it'd be cool to go out to Meteor Crater. And this was 30 years ago, better than 30 years ago. And we drove all the way out there. It was like $10 a person to get in, and thought, that's just a lot of money. So we turned, it was a big hole in the ground. So we turned around and left. So no, I've been to the outside of the visitor center, never actually been into it. So.
Oh, we've been twice, and the first time we got in for free because they hadn't set up everything yet. There was no visitor center. There was just a crater. You drove in, you got to look at it. So next time we went there, and by the way, the next time we went, they wanted $20.
Oh, wow, okay.
So we turned around. We didn't pay the $20 either.
It's kind of a shame because, well, anyway, that's a different discussion. But nonetheless, we find a lot of evidence of things that have impacted the Earth. And one of the more popular ones is the Chicxulub event. Not sure whether that's a reference to the crater or to the actual meteor. Never have found that answer there. But
the location is Chicxulub.
Fair point.
Yeah.
And so, we find lots of evidence that there's this impact event. And, something on the order of 10 miles in diameter. It hit 66 million years ago. We find a crater in the Yucatan Peninsula, or kind of just off the Yucatan Peninsula.
We're talking Mexico, right?
In fact, I got it's like here's the map. You can see it's down. You go down past Mexico, down into Central America, where it kind of the south side of the Gulf of Mexico. That's where the crater is. And I think the crater's on the order of 100 miles across. I mean, it's a massive crater. You'd expect that from something that comes in 10 miles across and hits with that sort of velocity. But why this particular event is known is that it also marks the end of the dinosaurs. So it's the Cretaceous Tertiary, that's not the right. It's Cretaceous
Paleogene.
Yeah, there we go.
Paleogene Cretaceous.
I know it's always the KT, and I always.
But now they changed the name. They call it Paleogene instead of.
But so it's 66 million years ago, the end of the Cretaceous period, start of the next period. And, because of the fascination we have with dinosaurs, a lot of people tend to know about this. But, as we were talking a little bit earlier, there's a question of what actually killed the dinosaurs, because there's this impact event that we can date to 66 million years ago. But then there's also a very large volcanic eruption that has occurred. And so the question is, was it climatic effects leading up to the crater caused by all the volcanoes that actually, so the environment, or I'd rather the ecosphere, the environment, what is that called where you get the collection of all the organisms? I'm just drawing a blank on the word.
Biosphere?
Yeah, well, that's not quite the word. We'll just use that one. The biosphere had been weakened because of all the climate change, and the impact event wiped it out, or did the impact event wipe it out and that caused the volcanic? And it's, so there's these questions surrounding that, because they both date very close to the same region of time. But what I found interesting in this paper is they were doing a study of what was the aftermath of the impact. Because, obviously you would expect the impact hits, throws a lot of stuff in dust and debris, makes a crater. But, something that's 10 miles on one side of the Earth, that it could have global consequences. What are those consequences? How long would it play out in there? And specifically what they were looking at was what were the effects to the solar radiation getting down to the surface of the Earth during this time. And so this is the paper, is the Chicxulub impact winter sustained by fine silicate dust.
Right.
And so in their investigations, you've got the, sulfates that are thrown up into the air that cause certain things. You've got dust thrown up into the air, and then there's a third one that I'm drawing a blank on. And so they're looking at just the impacts of these, and what they're finding is that it was hard to explain. Yes, it would have consequences, but were those consequences big enough to actually have caused an extinction event? And what I find fascinating about this is that, there's an abundance of evidence for this Cretaceous Paleogene impact event. You find evidence of the crater. There's elements, iridium that's scattered throughout the globe, from extraterrestrial impacts. So all sorts of evidence that an impact actually happened. But the particular analysis from this study was actually done by data that was extracted in North Dakota in what's called the Tanis region. And so, you got the Chicxulub crater down there. And the two pictures here, the one on the left is the current, how the Earth looks today in this region. The one on the right is how the Earth looked 66 million years ago. And what you'll notice is that there's this long inland seaway that extended all the way up into North Dakota and beyond. And that's the region where this event is being looked at. And why that's a fascinating region is, you've got this large event, happens in the water, so it's going to cause tsunamis that would flow up in there. They found evidence of a lot of, or at least this particular deposit that's emplaced by big waves, movements of water, but they find the dating or the timing of the event is that the formation happened within a couple hours, within 2 hours after the impact event. But for the tsunami to have reached that was going to take, on the order of a day, 18 to 24 hours for the waves to get up there. And so they're asking the question, how could we have had that much wave move or water movement if the tsunami hadn't gotten up there? And what they're theorizing, or what seems to make the most sense of the data, is that when the asteroid hits, it creates enormous earthquakes, 10 to 11 and a half magnitude earthquakes, which are enormous. It's not just 10, or it's not just, there's 9 and 10, that's about 10% larger. It's 10 times larger earthquakes than our magnitude 9 earthquakes.
Yeah, and a magnitude 9 will shake the bark off trees. So
exactly,
multiply that by 100 times.
Exactly, yeah. These are enormous earthquakes. But the earthquakes the seismic waves will cover that distance on the span of a couple hours. In fact, the shock wave, which will bring the debris along, the seismic waves are going to arrive about the same point in time. And so it explains how you get this particular formation. And so what you've got is the asteroid coming in, excavates this huge debris, sends out this ejecta curtain, and it's just side by side. Granted, this is, it's like about 3,000 kilometers away, North Dakota down to the tip of Mexico, if you will. And all this is deposited within a couple hours. And the particular region they're looking at is this point bar, which is this, you get these on the inside of a large meandering river. It's the inside of the curve where stuff gets deposited. And so there's this large point bar. And just for scale of what's being looked at here, that point bar extends, has a vertical displacement of about 10 meters. And it has a horizontal displacement, something on the order of 50 meters. And so you see evidence of this impact event, or the stuff being ejected from the blast wave and being deposited there. So you get the seismic waves that come along. They drive these large, I don't know, pronounce it. It's S-E-I-C-H-E. I'm going to call it Psyche for lack of knowing the proper way to do it. These Psyche waves will drive a whole bunch of debris up on there, cause these emplacements. And so it takes all of the material in there, and it actually, in the aftermath of the extinction event, you're going to get this large deposit. It turns out it's about a meter or so thick, or meter to 2 meters thick. So there's just a lot of material there to investigate. And what they were particularly focused on here, there's the silicate dust, there's the soot was the third thing, because in the aftermath, the collision is going to cause a lot of fires, but it ejects a lot of superheated debris, and as it comes and rains back in, it's going to start fires across the globe. And again, so you see a lot of soot. I think roughly 17% of the soot that was formed in the fossil deposits is from the impact. Something on the order of 85% is from wildfires that are started from other regions. So you got a lot of things going on here.
All those papers have been published years ago making the point that this impact ignited wildfires literally all over the entire planet.
Yeah, that's the contention in there. Right. But I mean, you do also have to remember there's only, 30% of the Earth's surface is that, land. And so you can ignite wildfires across all the continents, but there's more there. And so the whole point of that is that they're trying to figure out what in the world actually went on in the aftermath of this.
In the context of the dinosaurs.
In the context of the dinosaurs,
Right.
and in the context of, okay, so you got this large impact. Could this, I mean, yeah, you're going to have fires, it's going to cause stuff in the atmosphere, but will that just be, well, life's rough for a while, or could it actually cause the extinction? And that's what they're looking at in this. And one of the interesting things they found is that because they have so much material in this deposit, they were able to go through and investigate what are the sizes of the dust that has been scattered around, because we can get a pretty good measure on the amount of sulfur, the sulfates that are in the air, and how much they would reflect light and what that it would do. And it would have, kind of the effect on the order of about a year of what it would diminish the solar radiation that's getting down to the surface. You can talk about the soot, and there's less of that, but it's got a longer residence time. But it seemed like for the dust that it was going to be kind of a smaller player, because it would precipitate out more quickly, just because of, I missed a plot in here. There was another plot I had in here where they were looking at, typically the sizes are down around, micron sized or nanometer sized. And you can look at how quickly those precipitate out of the environment, or they're deposited out of the atmosphere. And those are deposited out at much quicker rates. You can make measurements of them. But what they found is that by studying the deposit on top of this point bar, they were able to get a better estimate of the size of the dust that's put up in there. And the way the plot looks, it's like the micron and the nanometer sized are much higher deposition rates. Whereas for the sizes that we would expect from this collision, they were actually at a much lower deposition rate. And so they would stick around in the atmosphere for much, much longer, which means they would have a much greater effect on how this particular impact affected the planet.
What are the time scales? I'm assuming we're looking at a few days for the small size stuff and several months for the bigger.
Well, so that's the short, the long answer is that when you get down to this, when they look at the dust is on the left side of this plot, and so it's dust and soot and the silicates, and
this answers my question.
And the combined. So what they're showing is that on the bottom plot, you see, the green and the white. That's the photosynthetic active radiation, and so the more green it is, the higher it is, and you can see what it looks like down at the bottom before the impact. Actually, they're able to determine that the impact happened in the spring of that year, which I find fascinating. I love the things that scientists can come up with. Day after the impact, you can see there's a little white blob around the Yucatan Peninsula where you just got stuff being sprayed up in there, lots of dust. There's wildfires and soots, and then there's also more sulfates being ejected. And so that causes a problem shortly thereafter due to all of that. But what you'll find is that the dust actually begins to dominate because it stays in the atmosphere. And so you have almost 2 full years where all photosynthetic activity on the planet has been shut down. And that 2 full years effectively means that there's
nothing for the dinosaurs to eat.
There's no source of food for anything. And so, for 2 full years, you can just wipe out any sort of food production or any sort of energy production. That does have the consequence that it could drive a global
it becomes
catastrophe.
Global literally within a few days.
It really does, yeah.
One day just southern North America, but by a few days it becomes...
It's a little hard here because we go from one day to the next year.
Right.
But what you see is that, the sulfates have a pretty rapid effect around the planet.
Right.
The soot and the dust have a smaller effect, but they continue and reside in the atmosphere a lot longer. And so the soot a year later is still causing problem. The sulfates have kind of largely dissipated. The dust is still there, and in fact, not only there 1 year, they're almost 2 years later, still causing these big problems.
And it shuts down photosynthesis, but also it's going to cause respiratory problems for big animals.
Oh yeah, no, and so I think I read a comment in there that almost any 4-footed mammal larger than 2 meters in size was nothing survived this, and so
they might actually die from respiratory issues before they die from starvation.
Right, but I just found this interesting, or what I found intriguing about this, or remarkable is that, one, we're able to put that detailed of a timeline of how quickly each of the the dust, the soot, and the sulfates, how much sulfate aerosols were impacting the photosynthetic rate on the ground, and to see just how long-lived that was. I mean, you're talking 2 years later for this
scales are
impact.
taking into account just the impact of the asteroid hitting in Chicxulub.
Yeah, this is just this is a climate model based on the aftermath of that impact.
So
event.
in reality, we're probably looking at something more severe because the impact ignited all those volcanoes in the Deccan Plateau, which is going to cause a contributing factor here, I presume.
Well,
Did they take that into account?
It depends on what types of eruptions the Deccan Plateau. Do they throw? They did say that's going to contribute a lot of greenhouse gases and other things like that, but that's going to be on the time scale of tens and hundreds and thousands of years.
But you're also going to get sulfur aerosols. You're going to get ash and dust. And we're talking thousands of volcanoes, so it's a big factor.
It is, but it's unclear to me, and I know they didn't include that in this analysis. So it would be an additional effect in addition to all this.
It's definitely going to make for a more severe scenario than what we got here.
Exactly. Although it could just do it in more local regions rather than global regions.
Sure.
That's a question that they didn't address in this paper at all. So,
well, this also explains, Jeff, why we see the detrivores doing so well during this episode.
That makes sense.
They got a lot of dead tissue to feed on.
A lot of stuff to work on. Yeah.
So they're doing okay.
Yeah.
But everything else is getting wiped out. Yeah.
And what this is one of the kind of apologetic significant, or the connection that I would make with that is, when you look at Psalm 104, which is a creation psalm that parallels what goes on in Genesis 1, there's this passage kind of in the context of, it seems like in the context of day 6, all creatures look to you to give them their food at the proper time. When you give it to them, they gather it up. When you open your hand, they are satisfied with good things. And then an asteroid hits and you hide your, that's my insertion there. You hide your face. They are terrified. When you take away their breath, they die. They return to the dust. When you send your spirit, they are created and you renew the face of the ground. That life was thriving on Earth before this impact event. This impact event happened and life was catastrophic. I mean, it just decimated in a lot of ways. But right after that, very quickly after that, life is thriving again, and a life that is more suitable for us being on the planet. And so, it's in the context of Psalm 104, you see God preparing the planet for us. Seems like with this impact event, we're getting a picture of some of the processes he might have used to prepare the planet for us.
Well, Jeff, I just got back from Asia, and in my audiences, this came up repeatedly.
Oh, yeah?
If there's a good God, why do we have these terrible mass extinction events?
Mm-hmm.
But I basically threw up this passage, Psalm 104. It says, notice it talks about God recreating.
Mm-hmm.
After every mass extinction event, there's a mass speciation event. And they said, well, why would God need to have that complicated of a process? I said, the sun's getting brighter. Mm-hmm. If the sun's getting brighter, you need God to remove life from planet Earth and replace it with life that draws more greenhouse gases out of the atmosphere. And only a mind is going to know how frequently these mass extinction events need to be, how intense they need to be, and what new life to replace the old life that goes extinct.
Well, I think that's a great point, and I find I did not appreciate just how dramatically Earth has changed from when it first formed to what it looks like today. I mean, there are just so many things we look and assume, oh, that's the way it's always looked. And, the atmosphere for the longest time was opaque, or not opaque, but translucent at best. And, for a long time that the oceans were filled with iron, and so they would look more green than blue. The life went from very simple forms to very complex life. You've got, the oxygen in the atmosphere increasing. You've got the solar luminosity being 30-40% dimmer and growing to what it is. All of these are major changes that could have radically impacted, or that could have made Earth uninhabitable. But, to your point, God is saying, hey, I know how this is going to play out. I'm going to orchestrate it so that it all works. And as the
All
planet
leading-
changes, the new things come in, and ultimately we can be here and enjoy it all.
Yeah, all leading up to the entry of human beings. And it takes a lot of careful preparation to create a window in which we can exist.
Right.
And that's Genesis 1, and that's what you're talking about here in Psalm 104.
Yeah.
think
Well,
it's-
and going back to what we were talking about, the universe is a pretty dangerous place for life.
But you
Earth is kind of almost unusual in how amenable it is to life. But even in the context of Earth being amenable, we see these same sort of catastrophic processes, but instead of wiping out life, it's preparing the planet for even more life.
And I'm amazed that we see just the right frequency, these big colliders, so that God can step in, create new life, and perfectly compensate for the brightening of the sun.
Yeah.
It's at the just right frequency rate of about every 35 million years, which is what you need to stay in tune with what's happening with the sun. And we benefit from all this. Look at all the biodeposits we have as a consequence of this long history.
Yeah.
And I'm amazed that some of the most valuable metals that sustain our civilization come from asteroids.
I know. That's where you get a lot of your iridium from. Iridium and osmium, which are two
Well-
really remarkable metals, are mostly extraterrestrial in that sense.
Well, 80% of the gold in circulation and 90% of the platinum comes from an asteroid. 50% of the nickel we have in circulation comes from an asteroid. So, but you don't want those happening every day, do you?
No, you don't. And, I think there's even a design element of how rapidly they happen. But,
Right, it's happening at
it
just the right
is just
rate.
fascinating to me how well orchestrated all that is. You can look at that as, well, why did God do this and kill everything? But really, it's this symphony that's all working together. You got these astronomical and geophysical and atmospheric and biological effects, and they're all working together. That in spite of all that has gone on, Earth has remained within about a 20 degrees Celsius window for its average global temperature for 4 billion years. That's
Right.
incredible.
Well, I like your symphony analogy because, you got all these different disciplines of science, and God's working in every one of them to bring about the end result. So,
Well, very good. I appreciate the discussion today, Hugh. And I want to thank you for joining us on Stars, Cells, and God. I want to encourage you to join us in the comments below. Remember to like this video. You can subscribe for more content. We release new episodes each Wednesday for Stars, Cells, and God. They're available on YouTube and on your favorite podcast app. I want to encourage you to share this video with your friends. And remember, the more we know about science, the more reasons we have to believe.